Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we discuss computations with arrays of data, including finding norm, dot product, or inner product, and simple cases of matrix multiplication. We also see the reason that NumPy is so important in the Python data science world. Finally, we establish connections with linear algebra operations and NumPy built-in functions. So if you're interested in these topics, please keep watching. NumPy, which stands for numerical Python, offers array computing, mathematical functions such as exponential and logarithm functions, and linear algebra routines such as dot product or inner product and matrix multiplications that we use these tools in every machine learning problem or project. And one of the important things about NumPy is that we work with multidimensional arrays. So in a simple case, we have a one-dimensional array, which means that this is shown here by this vector A. So this is a one-dimensional array, and we have only one dimension that contains an ordered list of these elements. So we have A1, A2 to AN. So this index shows the location of each element in that array. And we use this notation Rn to show that we have n real valued numbers. And a generalization of this would be a two-dimensional array, which we have on the right. And here we have one dimension that we call these rows of this matrix. And then we have the second dimension, which we call this column of this matrix A. So now in order to find each element in this two-dimensional array, we need two indices. One that shows where that point locates in the row index and the other one for the column index. So that's why this first element is A1, 1. And then this element here is in the first row and the column number M. So that's why it is A1M. And now we can similarly index this point here because it's in the row number N. We put N for the first index and it is in column number 1. So that's why we call this A and 1. And this element here on the bottom right would be A and M because it's in row number N and column number M. And in order to represent this two-dimensional array, we use this notation, which shows that we have a two-dimensional array with n rows and m columns. So the general rule is that the first one is the number of rows, and the second one is the number of columns. So from a linear algebra perspective, you can view a two-dimensional array or a matrix as just stacking or putting these one-dimensional arrays next to each other. So in this case, we convert a one-dimensional array to a two-dimensional array. However, when we are using NumPy, it is extremely important to differentiate between one-dimensional and two-dimensional arrays. In fact, I see a lot of time that when my students ask me about the error messages that they get when they run machine learning problems, it is as simple as cases that they just confuse a one-dimensional with two-dimensional array in NumPy. So that's why now we're going to talk more about how to implement NumPy in a Jupyter notebook. And in this video, we are going to use Google Colab, or the full name is Google Collaboratory, which is very look like a Google Doc file. And in order to create Google Colab, you can go to colab.research.google.com. And this gives you a notebook, which has this IPYNB extension. And then you can just name your Jupyter notebook that I called here NumPy. And we only work with the NumPy package here. So the only thing that you need to do is to import NumPy. And it is also common to save a space later on, and also for simplicity to call this import numpy as np. But if you don't want to, you can remove this part and just say import numpy. And remember that after this, anywhere that I'm using np, you have to use numpy. But this is just simpler, so we just use import numpy as np. And the nice thing about Google Cloud is that all these packages are regularly updated, so you don't have to be worried about using the right or most update version. And in order to check the version of your NumPy, you can always use np dot double underscores version, and then again double underscores, and this gives you the version that you are currently working with. And you can go to NumPy website and make sure that you are using the most up-to-date version. You can here also use Jupyter Notebook from Anaconda distribution, or if you want to write this in terminal, you can do that too. But Google Cloud is a great resource for learning Python, and also for getting familiar with data science packages and libraries in Python. So in order to create a NumPy array, one way to do so is by starting by a Python list. So I create a Python list and I put 4 elements in it, 1, 2, 3, 4. And now we can use NP, and remember that we imported NumPy as NP. We can use np.array and pass this list. And in this case, we can create a NumPy array. And here you can see that I printed the NumPy array, and also I'm looking at the type of this NumPy array. And this obviously gives me this ND array, which stands for n-dimensional array. And that's exactly what we're looking for here, an n-dimensional array created by NumPy. And you may be wondering why we want to convert a Python list to a NumPy array, what the advantage would be. And the reason we do this is that Python is very flexible in a sense that you can put any type of element in each of those locations in the list. For example, you can add numerical values and strings or any other type of objects you want. And although this is very flexible, it is not very efficient in general. The nice thing about NumPy arrays is that, as the name of the NumPy says, it's only for numerical values. So this will lead to a lot of optimized operations that will be really useful when we work with very large data sets. And I will show you one example later on at the end of this video. We can obviously also create NumPy arrays directly using NumPy built-in functions. For example, if you want to create an array with 4 elements that are all zeros, you can just simply use np.zeros and then the number of elements that you want. So here we use 4. We can also create 2-dimensional arrays. So in the second example, we are saying that we want to have 4 rows and 5 columns. And you need to also here pay attention to these double parentheses that we are using. So if you say np dot zeros 4 and 5, you will get an error message, and we don't want to do that. So you need to use these double parentheses here. So NumPy is very picky about these minor differences, and you need to make sure that you follow all of these rules. So after we created these, and we can obviously see that here we have a 1-dimensional array in the first case and a 2-dimensional array in the second case. So let's say we want to confirm this and make sure that we have created what we are exactly looking for. So that's why you can use this dot shape. So whenever you create your array, use array dot shape, and this gives you the number of dimensions and number of elements in each dimension. So in the first case, you see that we get 4 and comma, and then there's nothing there. That's what we call none. So this means that this is a 1-dimensional array, and in that 1 dimension, we have 4 elements. However, when we look at the second example, where we created a 2-dimensional array and we use dot shape, then we see that here we get 4 comma 5. So this means that now we have two dimensions. The first dimension has 4 elements, and the second dimension has 5 elements. And just to recall, remember that in the case that we have a two-dimensional array, the first dimension is determined by the rows of a matrix, and the second dimension by the columns, right? So that's why here we have 4 elements or 4 rows, and we have 5 columns. This is very important because when you're working with scikit-learn, which is specifically designed for machine learning uh, problems in Python, you will see that we mainly work with two-dimensional array, and each row is one training data point or training instance in your data set, and each column corresponds to one feature or attribute. So you'll see that being able to work with NumPy arrays and finding the number of dimensions is extremely important. And remember that here, when we are using dot shape, we are not using any parentheses in front of that. So that's exactly how you should use dot shape to find the number of dimensions. There are also other ways to create NumPy arrays. One thing that is very useful when you have like a for loop and you want to repeat the process multiple times, you can use np.arrange. And one thing that is important when you're working with NumPy or other Python libraries is that you need to look at the documentation that is available for each of these functions. So if you go to numpy.org and find this numpy.arrange, and remember that the reason that here it says numpy.arrange is because they assume that you import numpy without using import numpy as np. Right now, because we have done that, so this is technically np.arrange instead of numpy.arrange. And this gives you all the information that you need. And I'll definitely recommend you to read this documentation very carefully, because here it tells you that the starting point, if you look at it, is in a square bracket. So this means that the starting point is optional. The stop point is mandatory. There's also another option if you want to have a step parameter. So why is this useful? Let's say you're looking for numbers from 0 to 5 with a step size of 0.5. So in this case, as you see, we get all these numbers 0, 0.5, 1, 1.5, and so on. And one thing that is important is that the stopping point is not included. So that's what you see from here that shows that the starting point is inclusive, but the stopping point is exclusive. So that's why in both cases, we see that 5 is not included in the created list. And always remember that if you don't specify the starting point is always 0. That's because also indexing in Python starts from 0. So that's something to keep in mind if you are coming from a background of, for example, working with MATLAB or other scientific computing packages, because sometimes the indexing starts from 1. But in NumPy and Python, it always starts from 0. The other operation that is very important to use is using the reshape method. So when you created a NumPy array, for example, here we have np.arrange 18, which means that this gives me a NumPy array that starts from 0 and then 1, 2, up to 17. So I have 18 elements here because it starts from 0. And now when you say dot reshape 6 and 3, this means that you want to have 6 rows and 3 columns. So obviously here what's happening is that we are going to put 0, 1, and 2 in the first row, and then the remainder in the other rows until we put all the elements in this two-dimensional array. And here it is also important to make sure that the number of elements in this two-dimensional array is the same as the number of elements in the original array. Otherwise, you get an error message. And it's also easy to assign new values to each of these locations. So here, for example, we are saying that the element in location 1 and 2 We want to change the value to be 100. And remember that indexing starts from 0. So this means that 0, 1, 0, 1, 2. So that's sort of like the location that we are looking at. So the element in the second row and third column. And we set this equal to 100. And the reason that I put this example here, because something that is extremely important is that I created a new sort of like, array here, and I assigned this value 100 after we reshaped the original NumPy array. So now if you look at that first array that we had, which we call it G, we see that actually this element has been changed. It's the sixth element in that array has been changed to 100, even though we didn't directly change the value of any element in G. And that's because when you reshape a function, the reshaped version and the original version, they are saved in the same location. So this means that by changing one element of the reshaped version, you are also changing the corresponding element in the main or original version. And that's also another cause of problem, because you may not want to, at some cases, to change the original value, and because you have changed something about the reshaped version, then this will cause problems. So to keep this is always in mind, that if you just use that reshape and then you change values of some elements, that will lead to changing the values of the original array. So that's something to keep in mind here. And the other trick that I want to show you here as a bonus point is that if you want to reshape an array in a professional way, it is common to just use -1 for one of the locations. So what this means is that let's look at the one on the left. So we have an array with 18 elements, and we say that we want to have 6 rows and 3 columns, right? So that's like the straightforward to do this. But on the other hand, if you don't want to necessarily like calculate the number of rows and columns, you can just say that you want to have 3 columns and then ask NumPy to compute the other dimension. So how many elements you need to have in the first dimension. And obviously this is a simple operation because it is 18 divided by 3, which is 6. But it is common that if you want to write your code very fast, you can just put -1. And this basically tells NumPy that I am too lazy to compute this value, and please do that for me. So that's what we call it as the professional way to use the reshape function in NumPy. So now, after creating NumPy arrays, let's talk about important operations that we see in a lot of machine learning problems. And one of them is finding the norm, or what you're probably familiar as a length of an array. So we know this, that if we have an one-dimensional array that has n elements, x1, x2 to xn, and if we want to find the norm of this array, which we use this notation, it's simply squaring each element and then adding them together and then taking the square root. So you have seen this example in high school, that if you have a vector that has 2 elements, 3 and 4, and if you want to find the norm or length of this vector, you can just simply take the square root of 3 squared plus 4 squared, and this will give you 9 plus 16, a square root of 25, and this gives you 5. So obviously we can extend this to any number of elements, and that's the same type of formula, that you are going to square each element, add them together, take the square root. And you can write this function by yourself in Python. For example, we can use def, which tells Python that you are defining a function. You use a function name, which I call it vector norm, and then here the input is vector. And what we do is that we have a for loop that we are going to look at each of these elements, and we take them to the power of 2, and then we add them together, take that to the power of 0.5. which is equivalent to taking this square root. And that's the value we return. So obviously here, if I give this vector or one-dimensional array x, we see that the value that we get is 5, which is exactly the same as what we have here on the right. But in NumPy, we have all these functions built in, so we can just simply use them without being worried about implementing these things from scratch. So from NumPy, you can import this subpackage called lin alg, or it stands for linear algebra. And if you now use this linalg.norm, so that's why you can find the norm or length of the one-dimensional array X without writing your own function. So this is something that comes in very handy when you want to find norm of one-dimensional arrays as well as higher dimensional arrays, like for example, like two-dimensional arrays. Obviously, when we have a two-dimensional array or matrix, we have to be cautious about the way that we define the norm operator, and there are several ways to do this. So I'll explain that in a future video. But here I want to show you that if you have a one-dimensional array and you want to find the norm, you can just use this package called lin. The other operation that is extremely important in machine learning, and you see it in linear regression, you even see it in neural networks and deep learning, is dot product or inner product. So dot product or inner product is defined for one-dimensional arrays of the same length. So here I create a one-dimensional array X, which has two elements, 3 and 4. And then I create another one which has two elements, 2 and 3. So the first thing is that both of them have two elements in one dimension. So this means that they have the same length. And now we can find the inner product or dot product, which we use this notation. And one thing that is important to remember is that the inner product or dot product of two arrays is always a scalar, is a single number. And the way that you compute it is very easy. You just multiply elements in the same location, and then you add them together. So here we get 3 times 2 plus 4 times 3, which would be 6 plus 12, which gives us 18. So here we work with a with a one-dimensional array with two elements, but obviously you can use this when we have n elements in each array. So here if we have X, which has elements x1, x2 to xn, and then we have Y, which has y1, y2 to yn. That's the general formula for inner product and dot product. And I'd like to emphasize again that the result of inner product or dot product is always a scalar or a single number. And we can use, again, built-in functions in NumPy to perform inner product or dot product. And that's the part that, again, you can look at the documentation and make sure that you follow all the rules there. So here it exactly states that if you have two one-dimensional arrays, which we have here, then we will compute the inner product of those vectors. And remember that we said that a one-dimensional array is exactly a vector that we know in linear algebra. So obviously here you can see that we can use numpy dot for higher dimensional arrays, for example, like two-dimensional arrays, but that's not inner product or dot product. That's technically a matrix multiplication operation. So that's why it's extremely important to make sure that here, if you want to find the inner product, to use dot shape and make sure that they're both one-dimensional arrays. So now you may wonder what a matrix multiplication is. So in this case, let's look at one simple example that we have a two-dimensional array which has m rows, right? I see it from here that these two-dimensional array as m rows and n columns. So in linear algebra, we call this m by n. And then here I have a vector that has n rows and one column, which is n by 1. And if we multiply these together, the way that we can do this is that these two neighboring dimensions should be the same, which we obviously see that they're identical. And then the result would be another two-dimensional array with these dimensions, which is m and 1. And here is the things that that we have to be cautious about is that when you want to do matrix multiplication in NumPy, make sure that all these different arrays are two-dimensional. And that's here why I wrote this as n by 1, because we basically saying that we have two dimensions. In the first dimension, we have n elements, and in the second dimension, we only have one element. And this is different than a one-dimensional array because in that case, we would be n and none. That's what we talked about it before. So make sure that here, if you want to do matrix multiplication, they're both two-dimensional arrays. And that's like the general formula. So the way that it works is that for finding this first element here, you're gonna take the inner product or dot product of this row with this column. And you're gonna repeat this process. So here I have a simple case to show you exactly how this works. In order to find this first element, what we do is that we take the inner product of the first row and this another vector that we have in the front. So the result would be A11 times B11 plus A12, B21, A13, B31, and then A14 and B41. And you see here the general rule, right? So this number and this number, these two numbers, they're always identical. And you see it here in this equation too, that we have here index I, and then here we have index I. So we can repeat this process. I would recommend you to pause this video and try to figure out the next one. So for the next one, what we do is that we take the inner product between the second row and this vector here. So what this gives us is A21, B11, A22, B21, A23, B31, and then A24 and B41. And then for the last one, we see that we get A31, B11, A32, B21, A33, B31, and A34, B41. So even here, you see that these two neighboring indices are identical. So that's sort of like the simple case of this equation that we have here. And as you probably have seen in a lot of machine learning problems, using matrix multiplication is very common in any machine learning problem, including deep learning and neural networks that use a lot of these operations sequentially. So now let's look at how we can do this in NumPy. So in order to show you this example, I created a two-dimensional array which has 3 rows and 4 columns, like very similar to what we have here. Here we have 3 rows and 4 columns. So I'm trying to exactly replicate the same example. So that's the matrix A. So it's 0, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, and 11. And then we multiply this by a vector that has 4 elements, and they're all equal to 1. So this is A, this is B, and now we want to do matrix multiplication. So in this case, instead of using np dot dot, I recommend you to use np dot matmul, which means math multiplication, and then you give these two-dimensional arrays in the same order, because something that is important is that when you're working with matrices or two-dimensional arrays, you cannot change the order. So A times B is not equal to B times A. In fact, it's easy to show that B times A, this one doesn't even exist because of the rule that I told you about the fact that the neighboring dimensions should match. So that's something to keep in mind, that you should give them in the right order. So we have A and then we have B. And when you do this, what happens is that we find the inner product between these two. So that's how we find A times B. So this means that we're going to multiply each row of A by 1, and we just add them together. So this gives you 1 plus 2 plus 3 for the first element. And then for the second element, we get 4 plus 5 plus 6 plus 7. And the last one, we get 8 plus 9 plus 10 plus 11, which this gives us 6, and then 22 and 38. So to show you, after finding these, to show you why these matrix multiplications are super useful. So let's say that we are working on a data science problem and we have this huge matrix A that, let's say, has 1 million rows and some columns. So you have 1 million, let's say, users in Netflix, and you want to find the sum of elements in each row. For example, in this case, each column might correspond to a movie, right? So each column corresponds to a movie and the rating that that user has given to that movie. And you want to find the sum of ratings for each user to, do some data analysis. So in this case, one option would be to write a for loop, right, and read each row and add all the numbers together. But this would be very inefficient because you have to write a for loop to go over 1 million rows. Or you can use NumPy and just simply multiply this matrix A by another vector of appropriate number of elements that has all the elements equal to 1. So in this way, you find the sum of rows in just one matrix multiplication. And this would be a lot of computational savings when you're working on a really large scale problem. So that's why using matrix multiplication and linear algebra operations and these types of tools are extremely important for data analysis, machine learning, and data science problems. In future videos, we talk more about more complicated matrix multiplication problems and other linear algebra operations. So please don't forget to like and subscribe, and thanks for watching.